Welcome back. We're now in week 8. This is the first of 2 lectures this week. This is lecture 8A. Continuing on with mechanical considerations, we're going to be looking at preheating combustion air. Out in the field, there's a number of industrial processes that can produce large amounts of very high temperature exhaust gas. Some of this heat can be extracted and used to actually turn around and preheat the incoming combustion air. The following graphic demonstrates the idea. Here's the situation that we have initially. We have some sort of industrial boiler and/or process. It's bringing in combustion air. Now, depending on where it's taking it from, it may be taking it from the surrounding area, or it may be ducted in from the outside. Either way, we have a temperature of supply air for the combustion air gas. This is being heated up in here to do whatever process we're doing, and then we're exhausting very high temperature gas. In this case, we're exhausting gas at 2,600 degrees Fahrenheit. What we'd like to do is extract some of this heat from here, preheat the supply air here, as noted on this slide. So we have a heat exchanger both in the combustion air, we have a heat exchanger down in the supply air, and then we have some sort of fluid, oil, something that's tolerant of a real high heat that has an ultra high boiling point that we can circulate down and through the heat exchanger to transfer some of that heat. Now the equation for savings. It's basically a 3-step process, Step 1 is we need to calculate the preheated supply air temp. So if we go back to the previous slide, you'll notice that this is our supply of combustion air initially coming in. It's run through this heat exchanger. Now it's actually been preheated. So we actually have a preheated supply air going into the industrial boiler. We need to determine this value first. So that's step 1. Step 1, we need to get the fuel saved from a proper table. Now I've included those tables in your notes, so you have the proper tables at the end of your notes. Then we take that and we calculate savings. So again, 3-step process. Now there's 2 sets of formulas. The first formula is to calculate the preheated supply air temp. Now what we're going to need there is we're going to need the exhaust air temperature coming off the boiler initially, and we're going to need to know the initial supply air temp, which is whatever the temperature of that combustion air where it's pulling it from. This is multiplied by an effectiveness number. Now, heat exchanger manufacturers or high temperature heat exchanger manufacturers are the ones that produce the effectiveness number, which is really the efficiency of the heat exchanger. The typical number used, or the typical range of numbers, is about 55. So that's what we're going to be using in our example. But you can go to the heat exchanger manufacturer for these high temperature heat exchangers and get a precise number depending on your application. Now, once we get this preheated supply air, we take that along with the exhaust air temperature and go to a table, which we're going to look at in a minute. We bring that back after we calculate from the table a percent fuel saved, and then we can plug it into this bottom formula and get how much money we're going to save per year. So, step 1, calculate preheat. Again, effectiveness, this is the efficiency of that high temperature heat exchanger. On this application, we're going to assume 55 or 55%. Again, you can go to the heat exchanger manufacturer and get precise numbers. It just happens that most of them are about 55% effective or efficient. What you need is the original supply air temp. In other words, the temperature of the air where I'm pulling my initial supply air for combustion. I need the exhaust gas temperature and the effectiveness. And again, we're going to use 55. So here's our overall example. I have an industrial process. It's getting supply air from the surrounding area, which is typically around 74 degrees. The process is exhausting gas at 2,210 degrees, and the process is currently using natural gas. So that's important when we take it to the proper table. So given supply air temp 74, exhaust air temp 2210, process annual fuel use about 12,456 ccf. The fuel content per the 100 cubic feet is 100,000 BTUs, and they're paying about 49 cents per ccf. So step one would be to calculate the preheat of the supply air temp. So we take the exhaust air minus the supply air, and then multiply by the effectiveness, and then we add the supply air temp. So when we run through that equation, we get a preheated supply air temp of 1248.8. So you can say 1249. Step two, we need to get the fuel saved from the proper table. Use the proper fuel saved table, in other words, for the proper whatever you're using, whether it's number 2 fuel oil, natural gas, whatever. You need the exhaust air temperature and you need that preheated supply air temperature that you just calculated. Now, when getting the fuel saved from the table, you almost always have to interpolate. I know, that excites everybody. The interpolation exercise can be found at the end of the lecture notes. So let's have a look here. This is an example of a percent fuel saved table. Now this one happens to be for a natural gas situation. What you notice across the top, that's your preheated combustion air temp, or your preheated supply air. Along the left-hand column, we have the exhaust gas temperature. So what we do is we have to go across here until we find our preheated combustion air. And again, it's probably going to fall somewhere between these numbers. It's almost never going to fall exactly in a number. And we're going to have to come down here and slide across between our exhaust gas number. And all these numbers within the table, those are a percent of the fuel saved by preheating that combustion air. That's the percent fuel saved by preheating the combustion air. And you can see it can be fairly significant. Now let's go back to our example. We calculated our preheated supply air temp at 1249. Our furnace gas exhaust temperature was 2210. You'll notice that from that natural gas table, both these numbers fall between actual values. So this is my little interpolation table. What I do is I put the value of percent fuel saved for the 2200 exhaust gas temp at a 1200 preheat temp. I would save 38.8% of my fuel. Then I put in the high end. So in other words, I'm putting in the numbers that bridge both the preheat air and the exhaust air. So I put those four values in. Now what I'm shooting for is a value that's going to occupy this center square. So the bad part is that I'm going to have to do a double interpolation on it. So what you do is you do one direction first, then the final direction. So step one, if I look at the distance my exhaust temperature is, the total difference between things on the chart are exactly 100. And in my case, I'm at 2210 from the 2200. So in other words, I've moved 10 increments between an overall distance of 100 increments. So that distance over the total distance that I could travel, I simply set up a ratio, 10 over 100, which really makes it easy. So I'm 10% of the distance along this table. I can apply that same situation to this. So in this case, my total distance of fuel saved is 38.8 to 40.8. So that total distance is a distance of 2. I know I went 10% the distance here, so that means I went 10% this distance. So 10% of a total distance of 2 is 0.2. So I have to take that 0.2, add it on to my starting point. That means at 2210, my fuel saved is 39. Now that's at a preheat supply temp of only 1200. What I have to do now is move over to this category and do the same exact thing. Again, my distance from 40.9 to 42.9 is also 2. I've gone 10% from here. So again, 10% of 2 is 0.2. I add that on to the 40.9, so I get 41.1. So now I have the percent fuel saved at a specific exhaust gas temp. Now I have to figure out what distance I've gone in this direction. So I have to interpolate between the 39 and the 41.1. So if I look up here, my units between my starting point and ending point again are 100. In this case, from here to here, I've moved 49 points out of 100. So 49 over 100 is 49%. That means down here, I have to have moved 49% of this distance. So the distance between 39 and 41.1 is 2.1. I know I've moved 49% of that, so 0.49 times 2.1 is 1.03. I add that from my starting point, and I get exactly 40. This is my double interpolated percent fuel saved for the condition of preheat air 1249 and exhaust air gas of 2210. Now I can take that 40% fuel saved back here, multiply by my total fuel usage for a year, times the cost of my fuel, and again, because that's a percent, I have to divide by 100, because really it's 0.4. And my savings is the fuel that I saved, over the total fuel used, and I saved $2,441.38 by simply capturing heat coming off that exhaust gas and preheating my combustion air. So this ends the first lecture of week 8. So lecture 8A is complete. When you're ready, you can proceed to lecture 8B. Thank you.